thank you very much. This is going to be a talk about control of, and the pointer doesn't work, of course. Why it does not work?
Here, take mine.
No, I mean, this was working. I mean, it stopped. Ja. Es hat vor kurzem noch. Okay. Right. Okay, so this is going to be a talk about twisted light control in ferroelectric order in a Rashba-type semiconductor. And I'd like to emphasize I'm coming more from the experimental side. So I'm more experimentalist. And I always like to have a visual kind of interpretation of the physics, what's going on. So structured light or twisted waves or beam vortices, I like to have this representation of a rotating Poynting vector with energy flux going in that direction. So Poynting vector, and it propagates and rotates. This is very special. This lies at the heart of the beam with a beam vortex. And because this is going to be a talk about diffraction, you can already make very simple consideration pointing to a problem. And what is the problem? If we have a diffraction in a material, let's say this is a perfect lattice. Now you have this incoming beam and it should, let's say, scatter. Now because of this rotation of the beam vortex, we have, let's say, let's consider these two scatterers, 1 and 2. And now, because of this additional path the beam vortex is exhibiting in his propagation, there is also some additional d length to be considered, and you can very easily then figure out, aha, I might have issues with some coherence, because this scatterer and this scatterer, the scattering is not perfectly lined up. So this is a very first easy consideration, which already hints, yes, scattering and diffraction with OIM light is probably not going to be easy. Right, so what you see here is this rotating Poynting vector like it's shown in the front, and this is one cartoon image I found in a database. So somehow like this, I was imagining that I imagined that maybe this wave field would work inside a material which we now are going to explore with diffraction experiment. And as you can see here, I am pointing here to some electric field vectors which point in one direction, and the idea was here, okay, we have this additional path. The OIM is the beam vortex is exhibiting in diffraction, and if this additional path would kind of be a integer multiple of the wavelengths, and these wavelengths I'm going to talk about here are hard X-rays, so very short, 1 nanometer. Maybe we have some interference, and this interference will materialize as a unique direction for E field that would maybe act as a medium for polarization. Okay, this is all wrong. This was the hypothesis which we had to cancel out since the very beginning, because simply everything is averaged out, no effect takes place. And of course, the real picture is exactly as shown here, which is a tame average second order polarization spatial distribution along the germanium telluride 111 ferroelectric order. And here I'd like to directly refer to the next talk by Václav, who will explain you more details, what was our path into this understanding. But interestingly, you can see here there are these fringes here or intensities that very faithfully represent what is in this cartoon, and I am going to also mention these effects, how they, what is their role in the polarization. So this is my outline. Of course, this is going to be about beam vortices with zone plates generated, spiral zone plates generating the orbital momentum. It's going to be about nonlinear, non-zero time average OM effects in non-central symmetric GT111. And because the format of SPICE conference, as you see, is on the spot, is about spin phenomena, I am putting here into your attention this point 3, like harnessing spin charge dynamics with OM down to atomic resolution. This is a really strong statement, I guess, right? But this is the magic experiment which will do the job. Finally, I will also show you that we have significant structural changes in diffraction and nexus. And in the end, I will try to convince you that I'm talking about an efficient control of polarization in this system. Anyway, beam vortices, I think I can skip this because everybody knows already how does it work. We are using these spiral zone plates, which I got from a colleague of mine, Benedikt Rössner, who manufactured all these spiral zone plates during his PhD thesis. And I was asking him, Benedikt, can you just lend me for some fancy experiments? He said, well, yes, of course, why not? So here they are. And here I'd like to come to the point where the situation gets complicated. This is a paper which I was really trying hard to understand, paper by Konstantin. And it shows that a simple reflection of OM beam, there is a wealth of phenomena which makes it really difficult to understand what happens actually already when OM beam is reflected. So, for instance, here in this paper, you can learn about spin-orbit interactions of light, transfer shift. This is something very specific. It refers to the spin Hall effect of light. And I was thinking, okay, we have spin Hall effect, so this is a spin-orbit interaction. So if it just goes into the material, it will generate some voltage. Here we go. It's very simple. Actually, again, this was the wrong lead. Because if we now consider this medium, germanium tellurium 111, this simple cartoon model actually has to be translated into the second order response in the polarization, where these E fields do not wash out, and this effective polarization we will consider in this experiment is composed of two elements. Actually, this is a third rank tensor, and it has 27 components. And these are the tensors which really have physical meaning in polarizing in the direction which is 111. This is the out-of-plane direction of this material. GT111 is very, very nice in that it's a room temperature ferroelectric, and that's why it was used. Anyway, Václav will explain more details. Let me also explain you why GT111. This is a material which we were studying quite intensively for quite some time, and if you listen carefully, yesterday's talk by Ritesh, this is very interesting. It is a C3V point group, and there are very fancy optical phenomena that this material can produce. Among others, also this non-reciprocal transport. It has a huge shift current, 10 times bigger than, for instance, in barium oxide. And moreover, and here I'm making this connection to spin phenomena, these bulk states here, they are 100% spin polarized. And if we switch the polarization, we switch the spin. So all my presentation goes towards direction, all optical manipulation of the spins in this ferroelectric Rashba semiconductor with beam vortices. Okay, so I will show you just 3 slides that Václav will show you right after me. And the reason is that I'd like to highlight what happens when we consider this weak and strong component. What you see here is a series of projections of this P3 polarization before focus, right at the focus, and after the focus. And if we now engage the L1, so if we switch to the spin to the spiral zone plate, what we get is a bit different picture. Let me proceed to show you what happens when, and let me now go back. You can see here immediately that something happens here. Something is changing. And this is an effect which is not vanished, not averaged out. This is a real effect in this P3 component. Here is one more highlighted, that these intensities 1 to 3, they have different intensities along this focal direction. And for instance, if we are working in defocus, which we always worked, so we have good chance to have really high intensities in this rotation angle. All right, now let me very quickly show how this works, this polarization change in the material. Germanium telluride is a special ferroelectric. This is an electronic ferroelectric, not an ionic one, for instance, like a barium telluride, barium oxide. And it works. The switching is pretty well understood as a resonant bond switching between tellurium and p orbitals. And what you see here is a sketch how the polarization is changed through some transient state into a switch state. Let's say here we have this P3 component with weak polarization. Simply the bond lengths between germanium telluride swap, so the longer becomes shorter, and this is how the switch state materializes. And if we then rotate it, if we use the opposite OAM, then we reverse the polarization. So this is the mechanism. Now, there is one thing we have to bear in mind, and this is that the strong component is really strong. And it's mainly concentrated, really strong compared to the weak one, and it's really focused near the middle beam center, and this is why we employ a beam stopper in our experiment. So we, let's say, try to kind of screen this high intensity. This is my beautiful beamline where we did all these experiments. So this idea started, I think, back in 2020 during an experiment at Bessie. We were thinking how to make some fancy experiment, and Andrei will have a poster. He will explain you the more details on this setup. So eventually I realized that I have beamlined all the experimental equipment needed for this experiment, which is needed for the standing wave experiment, which is basically a fluorescence detector, nice diffractometer, this beautiful fine mechanical stages, and eventually this array of spiral zone plates by Benedict, where I can, let's say, set the OIM I'd like. And this is another busy slide. Again, I'd like to refer to Andrei's poster today. It shows the complexity of generating a standing wave in general. And for germanium telluride, this was a challenge because it is defective. And so Andrei will explain you how we managed to do that with a trick that is basically the template, the substrate on top of which germanium telluride is grown. And this template, indium phosphide or barium fluoride, serves as a perfect standing wave that is then detected in germanium telluride. Again, the main point is that if you measure these beautiful fluorescence dependencies in a diffraction in diffraction, so you have a perfect understanding of the phases which are atomically resolved, and this is the handle we have to the individual phases on the material, which we're now going to explore in OIM. Now, very simple experiment. Let's shine light, OIM light, on this germanium telluride, and repeat the Bragg scans through the Bragg angle at 11 kilovolts, which is the germanium K edge is around incidence. First order Bragg angle is around 8 degrees. And what you see here is really dramatic, what happens. Namely, let's shine first, and this is, let's say, 1.5 hours. I was doing following diffraction with a Fresnel zone plate, so no OIM in principle. And then, after these 1.5 hours, let me shine light with a spiral zone plate, and you can see here something starts to happen, and it's quite dramatic, because if we plot this series of simple Bragg scans in time, what we see here that the diffraction peak, full width half maximum, is getting down, and the intensity goes high. And at the same time, as I was taught by Václav, what you see here is an imprint of very specific dynamical diffraction, which takes place when the material is going to be perfectly crystalline. So what we see here is that in this time lapse, we started to polarize the material, and eventually we ended up in this polarized state with all the domains nicely lined up. And the similar experiment can be done also on other sample, and you see here that even this peak has systematic shifts back and forth, depending on the OIM light. So there is something happening. Absolutely no doubt. We are very likely polarizing the sample. There is one more thing we need to bear in mind in this experiment, and this is something which I mentioned already in the beginning, that the diffraction of the OIM light doesn't work well. What it means is that if we just observe what happens with this diffraction peak as we scan through the rocking curve, is that we have, let's say, an intensity which is due to the diffraction of the direct beam, and also some strike, which we realized is the diffracted OIM beam. And eventually we realized, in order to make a meaningful diffraction experiment, we have to leave a bit space to direct beam in order to get the standing waves in place, and this experiment works. So basically, this experiment is a very special case of OIM probe and direct beam pump. So these are the lessons learned, which in case you would like to reproduce this experiment, you have to bear in mind. Okay, results. Alternating OIM, what you see here is germanium telluride relative displacement in angstroms. These are different substrates again, and if I alternate the OIM, something happens here. It's evident, right? Let's check the distance here of the polarization. So the relative displacement of this GT. This is around, well, okay, let's say 0.2, 0.22. This is not the full ferroelectric switch. The full ferroelectric switch would mean that we displace by 0.3 angstroms. Okay, so finally, let me show you some sanity check data. We also played with applied bias control, and also the results were not very nice. Why this? Because this is a semiconductor. It's very leaky. So if you would like to polarize with applied bias this material, you better think twice. Another sanity check, let's do the same on centrosymmetric tin telluride. And you see here there is no effect in alternating OIMs. Now, full switching examples. We made a pioneering experiment at the CSAX beamline. Let me explain why. So at the optics beamline, we have a bending magnet, and in a bending magnet, we are diffraction limited basically only in the vertical direction. So what happens in the horizontal direction is basically incoherent. So we had this effect. I showed you these effects, these clear polling effects, but it was not ideal illumination of the zone plate. Ideal illumination like here happens at the CSAX, undulator, and what you see here are scientists at the CSAX, Mauro, Andre, this is Andreas Menzel. Mauro, always skeptic. He was always asking questions, this is a nonsense experiment, why am I here? But maybe I'll convince you right now. Let's say we alternate OAM with Fresnel plate, OAM Fresnel plate. This is the excursion we measure. Look at this, 0.3 angstroms. This is full switch. And this is how these phases of tellurium and germanium atom phase in perfect antiphase. So we have a real switch, complete switch. Alternating OAM, plus, minus, plus. Again, full switch, fantastic. Here I'd like to open a parenthesis. Again, I'd like to refer to the talk by Ritesh. I'm talking about polarization. Ritesh has a very good point, had a very good point yesterday. Polarization is very tricky. This material has not induced polarization because it has a self-polling. It has a built-in polarization. And Rafael Resta, together with Vanderbilt, as Ritesh pointed out, they really founded the principles of modern theory of polarization. And as I had discussion personally with Rafael a couple of weeks ago, he told me that, I mean, spontaneous polarization is basically not computable. It's a huge problem. You have to go through this Berry phase. And this is the main message. It has to be defined by means of differences of polarization. This is exactly what we see here. You can see here how this difference in polarization builds up as a control of the OIM. Are there other experimental evidences? Let's check how this chemical shift works. So if we move the ions, of course, chemical shifts should materialize as shifting this KH. And here are the data. Let me just first draw your attention to this OIM-L0. Nothing happens here in shifts. And here when we alternate OIM, +1, and why not +3, +1, there is a very clear shift of the KH. The same happens also here, plus, minus, or -3, +3. So evident shifts, evident chemical shifts, and this must be related with the atomic displacements. Finally, let's try to understand what happened in Nexus. And here enters Jano into the game, proudly showing his cluster in Pilsen. This was before the hack. Now it's probably not as happy as now. But let's make this experiment. Let's think about the following experiment. As I explained to you, this polarization goes from one, let's say, up state through some transient state into the down state. And I was asking Jano, okay, let's try to calculate, can you calculate me this series of Nexus spectra as this germanium atom just makes this travel, let's say, from up to transient to down? He said, of course, no problem. This is absolutely trivial. Here are the data. And we can now consider simple difference spectra, like shown here. Let's say, what happens under a half switch, like I go from up to transient or from down to transient? This is what we measure. Now we can ask ourselves, what happens if we make a full switch from up through transient to down? This is what we should obtain. All these spectral features, 1, 2, 3, till 5, Can we see exactly this scenario in our experiment? The answer is, of course. It happened exactly during this transition, +1, -1. These are the NextSAFS data experiment, and this is theory. All 5 peaks nicely reproduced and flipped. This is a full switch. So, conclusions. I think I demonstrated, I convinced you that we have really in operando handle of the polarization with OIM beams down to atomic resolution. I also demonstrated this full switching in NextSAFS. The polarization control mechanism, and this is the long path during which also Konstantin helped us really to put us on the right track. This is the second order, lies in the second order ferroelectric susceptibility tensor response to orbital angular momentum. And this manifests as a angular rotation of the P3 polarization along this ferroelectric direction, which is ferroelectric active. And as Václav will explain in a minute, there are these strong and weak components we need to consider. And importantly, the switching process I showed is notably slow. It's not like on-off. And the reason is that there are maybe 2 main reasons. First, as I explained, we had to let a bit of direct beam going through in order to record these diffraction peaks. So there is a portion of the non-OIM beam which is acting as a background. At the same time, as Ritesh already pointed out, the C3V point group symmetries, there are photogalvanic effects taking place, and we simply cannot affect this bulk photovoltaic effect which is in the background. And this is something which we are working on because we would like to understand whether this is how it is working under OIM. I believe it is not OIM sensitive, so the P3 is the reason why we observed these polarization changes. And finally, my collaborators, Ondrej, Václav, of course Hugo and Mauro, our sample grower Gunther, Jano, our main theorist, and as I mentioned, the spiral zone plates are from Benedict. This is when he was working on the Christian David group, and of course, thanks also to Kostya for useful comments. So you are now officially in as a collaborator. Thank you for your attention.